Particle physicists may have just discovered a glue ball. In this video, we will come to understand what glue balls are, how they can be produced and isolated, and why the results of a lesser known particle physics experiment in China are so intriguing, innovative, and exciting. The Large Hadron Collider often steals the particle physics limelight. It is, after all, the most powerful hammer we have for testing the Standard Model, humanity's best model of the behaviour of the universe at the smallest of scales. However, the Large Hadron Collider is not the only machine, nor regularly the best, for shedding light on the remaining, long-standing, and frustrating dark corners of that Standard Model. Since the theory of quantum chromodynamics, or QCD, our framework for the understanding of the strong interaction, was finalised in the early 1970s, physicists have predicted the existence of an intriguing, fleeting, and unique class of particles that have so far never been observed. These particles are bound states of only gluons, the bosons that mediate the strong interaction, so-called glue balls. The Standard Model insists that such glue balls must exist. So where are they? Well, now, the BESIII collaboration in Beijing, China, may have the answer. BESIII scientists claim that they may have caught a glimpse of one of the lightest glue balls predicted by the Standard Model. For those obsessed with the discovery of new particles, your wait may finally be over. Just realise for now that if we can produce and isolate glue balls in particle physics detectors, we can again bolster the Standard Model, a framework that has withstood the assaults of experimental testing with such dogged resilience. However, if they continue to elude us, something else is going on. A potential chink appears in the armour of that framework, a chink that could let in the light of new physics. Searching for glue balls is a win-win. So what on earth are glue balls? Glue balls are a unique and unconfirmed prediction of the Standard Model. For particles or objects to interact electrostatically, they must carry charge. For example, a positively charged proton attracts a negatively charged electron. Electrostatic interactions are mediated by photons, acting between sources of charge, and there are two types of charge, positive and negative. By contrast, to form composite particles like protons and neutrons, quarks must interact via and be bound together by the strong interaction, mediated by gluons. Quarks and gluons interact via the strong interaction because they carry a different form of charge, known as colour charge. Colour charge comes in three varieties: red, green, and blue. Note that colour is an internal property or label of a quark or gluon, and unrelated to any outward appearance. Redness, blueness, and greenness could just as well be called oneness, two-ness, and threeness. In quantum chromodynamics, our theory of the strong interaction, we never, ever see colour-charged particles in isolation. All free particles are colourless. That means that we never observe free quarks or gluons. They instead have to clump up into colourless combinations, a phenomenon known as colour confinement. This confinement constrains the way that a bound state can be created from quarks and gluons, the particles that carry the colour charge. The framework of visual colour provides an extremely powerful visual aid for understanding the colourless packets that quarks can form. Nature can form baryons with 3 quarks each, like the proton and neutron, in which there must, at any instance, exist one red, one blue, and one green quark. Red, blue, and green combine to make the baryon colourless overall. Nature can also form mesons, composed of a quark-antiquark pair, like the pion, containing at any instant one red, green, or blue quark, and one anti-red, anti-blue, or anti-green antiquark. Colour and corresponding anticolour combine to create a colourless meson overall. Baryons and mesons are examples of colourless 3 particles, known as hadrons. In the last decade, we have also learned that nature combined together quarks in exotic combinations of the packages outlined above, for example into tetraquarks containing 2 quarks and 2 antiquarks, or pentaquarks containing 4 quarks and 1 antiquark. However, in all of these combinations, colour confinement is obeyed. The overall combination is colourless. Okay, but where do glueballs come in? Well, the photons that mediate electrostatic interactions do not themselves carry charge. However, the gluons that mediate strong interactions do carry colour charge, 1 unit of colour and 1 unit of anti-colour. That simple realisation means that we should be able to take 2 or more gluons and combine them in such a way that the overall combination is colourless. For example, if we combine 1 gluon with 1 unit of red and 1 unit of anti-blue, with 1 gluon with 1 unit of blue and 1 unit of anti-red. These colourless particles composed of only gluons but no quarks are known as glueballs, and the standard model of particle physics predicts that they must exist. So, if glueballs are a basic, fundamental prediction of the standard model, then why haven't we ever seen one? Well, the problem is that theoretically determining the properties of glueballs, and hence knowing where to look for them, is incredibly difficult. Indeed, calculating the expected properties of glueballs was too daunting of a task for even late 20th century physicists. When particle theorists perform calculations in quantum electrodynamics, they rely on so-called perturbative methods. The QED coupling constant between charged particles and photons is so small that more complicated descriptions of a QED process, involving a greater number of couplings and more complex Feynman diagrams, contribute less to the overall probability of a process occurring. Hence, theorists only have to look at the simplest Feynman diagrams that could underlie a physical process to get a good handle on it. Higher order diagrams contribute less and less. However, in quantum chromodynamics and in strong interactions, the coupling constant between quarks and gluons actually rises at lower energies, and more complex interactions and Feynman diagrams contribute more to the description of a QCD interaction at low energy. As such, traditional perturbative methods fall down and cannot be used for low energy QCD predictions. Calculating the properties of bound gluon states means performing QCD calculations in this low energy, non-perturbative regime. These calculations can only be done accurately by using approximations and incredibly powerful computers. They were impractical even towards the back end of the 20th century, but not now, with radical leaps in computing power. In the modern day, theorists can use numerical methods such as lattice QCD to simulate low-energy QCD interactions and predict the properties of bound states such as hadrons and glueballs. In lattice QCD, space-time is treated as a discrete grid with a very small inherent spacing. QCD variables are determined at points within the lattice for various lattice spacings, and the results obtained are then extrapolated to an infinitesimally small spacing to approximate QCD interactions in the real world. Lattice QCD predictions have already successfully agreed with many real-world experiments. For example, lattice QCD predicts that the transition from confined quarks to a quark-gluon plasma should occur around a temperature of 2 trillion Kelvin, an estimate that aligns with experimental measurements. Lattice QCD can also predict the masses of bound states of quarks and gluons. The mass of the proton has been determined theoretically with an error of less than 2%. The upshot of the ongoing meteoric rise of lattice QCD is that the masses and properties of glueballs, bound states of only gluons, can now be determined from first principles. As recently as the 20th century, experimentalists would have had no idea about the masses of hypothetical glueballs, and hence the experimental energy ranges in which they might appear. Now, lattice QCD can tell us exactly where we need to look and what we need to look for. As such, there is a rich, recent literature concerning the properties of glueballs and how they might be found. And there have been various claims that a glueball was on the cusp of being found, claims that are still not confirmed almost a decade after they were made. However, as lattice QCD methods and calculations have become more efficient and accurate, theorists have become ever more precise in their predictions regarding the properties of potential glueballs. Recent theoretical results from lattice QCD related to a specific class of glueballs published in 2019 predict that a light glueball should exist with a mass of 2.395 giga-electron volts. This particle is the lightest pseudoscalar glueball, meaning that it also should have a spin of 0, a parity of -1, and a charge parity of +1. Those latter two quantum numbers are intrinsic labels that constrain the ways in which it can be produced and decay. The upshot of all of this is that in 2019, lattice QCD provided a clear signpost as to where a glueball might be hiding. It was now on experimentalists to hunt it down. Of course, just because theoretical calculations can tell us the hypothetical properties of glueballs, that doesn't mean such particles actually exist in nature. So how can we go about creating and isolating glueball candidates for study? The best way is to smash particles together with enough energy to copiously produce a particle slightly heavier than the predicted glueball mass, a particle which then decays to produce gluons frequently. This is something the Beijing Electron-Positron Collider 2 excels at. The BEPC-2 has a circumference of 240 meters and has been in operation since 2008. The center of mass energy of the collider can be carefully tuned up to a maximum of 4.6 GeV. That's a factor of 1,000 lower than that of the LHC, but perfect for creating a huge number of BESIII particles, which have a mass of 3.1 GeV. Particles that are slightly heavier than the mass of the predicted pseudoscalar glueball. BESIII particles consist of a charm quark and a charm antiquark, and decay to a photon and a pair of gluons about 9% of the time. This setup is ideal for searching for the lightest pseudoscalar glueball, as the gluons from the BESIII decay can momentarily interact to form a bound glueball particle, and we are just around the right energy range to create the pseudoscalar glueball, according to theoretical calculations. The BESIII detector at the collider is the greatest factory ever constructed for investigating the BESIII particle. By the end of 2023, the BESIII collaboration had over 10 billion BESIII particle decays to study, and that may have allowed it to finally pin down an extremely rare resonance, the popping into existence of a fleeting, transitory particle, the presence of a glueball. So it's clear that the Beijing Electron-Positron Collider and the BESIII detector provide a superb, low-energy environment for looking for the glueballs predicted by recent lattice QCD calculations. And BESIII now claims that they may have just found one such glueball. So how did they do it, and what did they see? Well, the problem with knowing if you've created a glueball is that QCD is very, very, very messy, with scores of quarks, antiquarks and gluons flying around. The gluons from the decay of the BESIII can combine with other quarks and gluons to produce scores of short-lived resonant states, scores of particles. The gluons from the BESIII decay can even spawn quark-antiquark pairs, and these particles can momentarily bind to produce even more short-lived resonances that last for a tiny fraction of a second and barely move between being formed and decaying. How then can we disentangle all of these short-lived resonances spawned when a BESIII decays and uncover a hiding glueball? Well, BESIII scientists looked at the decays of a BESIII through two long decay chains. In both decay chains, the BESIII particle decays to a photon, two K-short particles, and an eta prime particle. The K-shorts then decay to two pions, and the eta prime decays to a photon and two pions, or to two pions and an eta particle, with the eta particle then decaying to two photons. These final state pions and photons stream through the BESIII detector, and their momentum and energy can be measured thanks to their curvature in the magnetic field of the detector and the deposits they leave in electronic calorimeters. By working backwards up the decay chain from the final state debris, scientists can combine the energy and momenta of the tracks in the detector at various points in space and reconstruct the mass, energy, and momenta of particles that must have existed but then decayed. By doing this sequentially, they can reconstruct the entire decay chain of the original BESIII particle and determine the masses, momenta, and energies of all the particles involved in its decay chain. However, when the momenta and energy of the two K shorts and the eta prime particle in the chain are combined, they indicate that the mass of the particle they came from displays the following distribution. This is clearly not the signal of a single particle. That would show up as a singular bump, as in the infamous Higgs discovery plot. What is happening here is that numerous different short-lived particles are being formed when the BESIII decays into gluons, and these short-lived particles are then decaying to produce the K shorts and eta prime. We are seeing the mass peaks of numerous intermediate resonances or particles all jumbled together. Many of the contributions to this mass plot are from well-known particles that have been seen before, such as the X1835 and the eta C. There also appears to be a broad, as yet poorly characterized resonance known as the X2800. However, BESIII scientists found that to fit this distribution of masses with exquisite accuracy, they had to include a small contribution from another well-known particle, the X2370. If the X2370 contribution is not included, the quality of the fit to the observed data plummets. The statistical significance of the X2370 contribution is a stunning 11.7 sigma. In layman's terms, this means that there is a vanishingly small chance, less than 1 in billions, that the X2370 is not being produced in BESIII decays and contributing to the mass distribution. The X2370 must be being produced in BESIII decays before rapidly disintegrating into K shorts and an eta prime particle. The X2370 is not new. It's a particle that has been observed with high statistical significance in completely independent analyses using completely different decay channels. Okay, that's all very interesting. The BESIII is decaying to a bunch of short-lived resonances, one of which is the X2370, which is then disintegrating into 2K shorts and an eta prime particle. But what the hell does this have to do with glueballs? And why are scientists so interested in their results if the X2370 has been seen before? Well, notice the mass of the X2370, which the optimization algorithm determines provides the best fit to the data. 2.395 plus or minus 0.01 GeV. Now recall the mass of the pseudoscalar glueball predicted by recent lattice QCD calculations. 2.395 plus or minus 0.014 GeV. Perfect alignment. And what's more, given the significant contribution of the X2370 disintegration to this data, BESIII scientists have been able to measure the quantum numbers of the X2370 for the first time. The intrinsic spin of a decaying particle has a profound impact on the angular distribution of the particles it decays into. Put simply, if a particle has a particular spin, its decay products stream out in specific directions, on average. By measuring the angular distribution of K-short particles shooting out from the jumble of resonances produced by BESIII decays, alongside other angles, scientists were able to determine that the spin of the X2370 must be zero. The X2370 is a scalar particle. Assigning different spins to the particle meant huge drop-offs in the quality of the fits to the angular data. The angular data doesn't make sense unless X2370 has no spin. Given the known quantum numbers of the other particles in the decay chains of the BESIII, scientists also determined that the X2370 has a parity of -1 and a charge parity of +1. These data conclusively support the hypothesis that the X2370 is a spinless particle with exactly the mass and quantum numbers that would be expected of the lightest pseudoscalar glueball. At first glance, we now have incredibly compelling evidence that the X2370 is that glueball. The alignment between theory and experiment is striking. So if we're extremely confident that we've discovered a resonance that has exactly the mass and exactly the quantum numbers that are predicted for the lightest pseudoscalar glueball by lattice QCD, why can we not declare that we've made the groundbreaking discovery of a glueball? Is this just scientists being overcautious? Well, not quite. The properties of the X2370 are consistent with those of the lightest pseudoscalar glueball from lattice QCD, and the overlap of the masses is incredibly compelling. However, that doesn't mean that this resonance, this particle, is the lightest pseudoscalar glueball. As we have seen, QCD environments are incredibly messy, with lots of temporary resonances contributing to the mass spectra that we see. It's conceivable that the X2370 could be another resonance between quarks and/or antiquarks, and not a glueball at all. There is also another nagging doubt raised by BESIII's experimental data. BESIII's findings indicate that an X2370 particle is created once in every 76,000 Japes-I decays. However, this production rate is currently an order of magnitude off when compared to the glueball production rate predicted by lattice QCD. This seems to indicate that the X2370 is not a likely glueball candidate. However, the accuracy of these production rates is currently up for debate, and theorists and experimentalists are now reviewing the underlying sources of this production rate tension. The bottom line is that we have a lot of circumstantial evidence that is consistent with the interpretation that X2370 is a glueball. However, there are also hints that its production and decay may deviate from standard model predictions. Therefore, we do not have a smoking gun for the existence of a glueball yet. So what steps need to be taken to nail down whether the X2370 really is a glueball? Well, they say that if something looks like a duck, swims like a duck, and quacks like a duck, then it's probably a duck. And the same idea holds here. If the X2370 really is a glueball, then it should be created in particle collisions at a rate that aligns with standard model predictions. So we need to clean up that production rate tension that we just mentioned. The X2370 should also decay to various final state particles with well-defined rates, which again align with the standard model. We should also not observe any contribution from the X2370 when studying decay channels that forbid the creation of pseudoscalar glueballs based on the quantum numbers of the other particles in the decay chain. Since the Higgs boson discovery was announced in 2012, LHC scientists have spent more than a decade checking that the particle behaves exactly as we would expect within the framework of the standard model. They have checked its decay rates to numerous final states and its couplings to numerous other particles. So far, the Higgs boson looks like the simplest standard model Higgs of theory. It has passed every test. The X2370 needs to be subjected to the same rigorous scrutiny. It needs to stand up to a rigorous battery of tests and needs to behave exactly as a glueball should on all fronts. At this stage, we can be confident that the X2370 is a real particle and has the mass and quantum numbers consistent with theoretical predictions for a glueball. But we need to do far more work to determine its exact nature and behaviour. There have been several false dawns in the field of hadron spectroscopy. Many calculations and overzealous claims that have suggested the glueball was on the cusp of being found, some of which have potentially harmed the external view of the fascinating, vital and vibrant field of hadron spectroscopy. We need to make sure that not a single hair on the head of the X2370 is out of place. We've waited more than 50 years for the glueball. We can wait a little longer. BESIII has presented evidence for the most compelling Glueball candidates to date. We may finally be on the cusp of verifying the existence of a species of composite particles that the Standard Model claims must exist, but which for more than 50 years have evaded observation. However, far more work still needs to be done to determine the full nature of the X2370 and to check that it measures up. Further work in this field is a win-win. If no glueballs exist in all of nature, then something new, unexpected and revelatory is wrong with the Standard Model. We gain a vital signpost for new physics. However, if glueballs do exist, the Standard Model, our best model of the universe at the smallest of scales, will again be bolstered. The exquisite work of the BESIII collaboration shows that groundbreaking particle physics discoveries are not the exclusive domain of the Large Hadron Collider and the highest energy accelerators. Sometimes a scalpel works better than a hammer. With proposals for a future high-energy particle collider in Europe currently under intense scrutiny, we may soon be looking to China and the CEPC for even more cutting-edge revelations. I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Before we finish today, I'd also like to give a couple of shout outs. Firstly, thank you to Dene Hoffmann. Dene is a physicist at Carnegie Mellon University, working on the GlueX experiment at Jefferson Labs. Dene helped me to understand the work of the BESIII collaboration and to dive into hadron spectroscopy. His guidance and fact-checking were invaluable. His work and socials are down in the description. I'd also like to shout out Lionel Lenoir, who continues to send me tips and support. They are very, very gratefully received. Thank you. Thanks for watching. Thanks for being scientific. Thanks for being bad.